2021, in 2021, moved to Valencia for a postdoc with the grant for Invisible, right? And then now he's still in Valencia at the Institute for Fisica Corpuscular, IFIC, with a fellowship from the Generalidad Valencia.
Yes.
And he's involved in research with the group SOM, que means sobre...
Sabor e origen de la materia. Sabor e origen de la materia.
Sabor e origen de la materia. In the IFIC, the Institute for Physical Corpuscular. And he's been working, successfully on many things, especially dark matter, also axions, neutrinos, and he's also interested in moving a little bit more toward phenomenology. And then we're having some discussions now, and also with other collaborators in Frascalia. So maybe I'll let him talk now. But, all right, thanks. Thank you.
So thanks, Maurizio, for the invitation here to Saragossa and for the presentation. Yeah, so it's nice to be back here. I already been in Saragossa, but it's the first time at university, so yeah, it's nice to visit here. Also, the weather is good. So after the last weeks in Valencia has been difficult, so yeah, not bad to have some good weather. So I have to say it's the first time I give this kind of talk, which is a bit mixed for advanced researchers and students. So I try to calibrate a bit. I think I will be mostly pedagogical. I try to keep it as simple as possible, the discussion for the students. So of course, if you have questions, you can ask me, interrupt me. Even in Spanish, if you want to ask questions, it's okay. So I will discuss about something more theoretical today. So the so-called action quality problem. So I will try to overview a bit what is the essence of this problem and some possible solution. But I will mainly focus on overviewing the problem. Yeah, and just the last part about solution will be a little bit more technical. So I will try to be faster. So I will start just reviewing what is the strong speed problem, what is the axion, why we need actions, and so on. So the strong speed problem can be formulated in a very easy way. And basically the essence is that if we look at QCD, so the theory of strong interactions, so if we look at the Lagrangian QCD, we should expect that strong interaction should violate the CP symmetry. And the reason for that is that the QCD Lagrangian, if we write all the possible allowed terms in the Lagrangian, should contain this term, which is called the theta term. So this term is gauge invariant, so respects all the symmetry of the QCD Lagrangian. It's even renormalizable. And even though, so this G is the gluon field, so this structure here can be written as a total derivative, but despite of this, the structure of QCD vacuum is very complicated and assures that this operator has non-trivial effects. So one naturally, so when operator is allowed by all symmetries, one expects that the coefficient in front of the operator is theta, it's a number, a coefficient, expect that is not suppressed by anything. So there is no reason why this coefficient should be suppressed, so one expects a coefficient of order 1. Yeah, notice that this operator is CP violating, so it's violating parity. So the analogy with electrodynamics, this operator can be thought as a electric time magnetic field. So chrome electric times chrome magnetic field. So this object from electrodynamics is known as that violate parity and CP. However, we know that there is a well-defined prediction, and a non-zero theta angle predicts non-zero value for this quantity, which is the electric dipole moment for the neutron. Okay, so it's a measurable quantity. That, okay, this is the Feynman diagrams that one can use to compute this. Some people did this in the 80s and find that this electric dipole moment is somehow proportional to the value of this theta angle. So large theta means that there should be a sizable dipole moment for the neutron. However, along the years, people try to measure this quantity, And really there's been a great improvement on the precision of experiments along the years. And yeah, so you see that today we have a very strong bound. So these are the actual upper bound along the years. And you see that today the bound is very strong. So if we translate the bound on the dipole moment on the theta angle, then we found that this theta angle should be smaller than 10 to the minus 10, which is an extremely small value. So this is somehow the essence of the problem, no? So why this parameter is so small? So we expect an order 1 parameter from the symmetries of the theory. So no suppression, there is no reason, no mechanism for suppression, but it turns out experimentally was extremely small value. Okay, so let's try to explain this. And so the most simple solution to this problem, it's very simple. It's the Peché-Quinn mechanism introduced in the 70s. So the idea, we have our standard model. We know that it works quite good. But so we extend the standard model. We consider a new U1 symmetry. So what does it mean? We consider a new field, a new complex scalar field that transforms under some global symmetry. So for the moment, I just put the symmetry. Then we see that the origin of the symmetry will be problematic. But for the moment, just forget this. And let's say that we have some global symmetry given by end, and with some field that transforms non-trivially under this. So this symmetry should satisfy some requirements. So first, it must be spontaneously broken. And okay, this is somehow easy. We have a scalar field charged under this. So this field, we can write a potential for this field, like for the x. So you'll find the usual Mexican net potential. And so that this field can acquire a value on the vacuum, a vacuum expectation value. So this Fa, which is known as the Peché-Quinn or the axion scale. So at this scale, the Peché-Quinn symmetry gets broken. And so we can parameterize the field like this. So the scale times some exponential that contains this field A. And if we see how this field transforms under the Peché-Quinn symmetry, so if we plug this parameterization here in the transformation, you see that the field transforms as a shift. So under the Peché-Quinn, the field gets a constant shift. So it's a Goldstone boson, okay? So this is what is referred as the axion. So in absence of any explicit breaking, so we have to respect this symmetry. This means that the Lagrangian, the interaction of the axion, can only contain derivatives, because only derivatives of this field are invariant. No? So very easily, no? If we write a kinetic term, a derivative, this is, okay, we miss an A, but this is clearly invariant under this. But if we write, for example, a mass term, this is not invariant, so this is not allowed. So up to now, we have just a theory of a massless guy, which is interactive with only derivatives interactions. Now, the interesting part is the second requirement, that the symmetry must be anomalous. So let's see how to explain in a simple way. So I will try to explain with a simple example. Okay, so probably the simpler possible axiom model. So it's called KSBZ, so the name of the authors of the paper. So the idea is very simple. We consider a scalar field, which is a singlet under QCD, so it's not color. And have some charge and this U1 symmetry. So in this model, for the moment, we just impose this symmetry, okay? We believe that there is a symmetry of the model for some reason. So the field is charged, but we also introduce some new fermions. So left and right-handed fermions, which have color, so are charged under QCD, and have charge under the Peché-Quinn symmetry. In particular, these two fields form a Dirac pair, but the left and the right component has opposite charges. So this is what is called an axial symmetry, or chiral symmetry. So if we do that, if I'm too slow or too fast, just interrupt me and tell me, because of course for part of the audience I'm doing very slow, for the other part maybe fast. So just please interrupt me if you want. So if I write down the Lagrangian for this theory, so I cannot write a mass term because it's for the fermion. This is forbidden by the symmetry. But I can write a Yukawa interaction, so the fermion with the scalar. So when the scalar gets a web, so take the symmetry, this gives rise to this kind of operator, which looks like a mass. So if we don't have this phase, this will be exactly a mass term for the fermion. But we have this additional phase in which we have the axion field here. So how we interpret this? Well, we can do a rotation. So we can somehow redefine the field with this kind of rotation. And if we do this, which is basically a Peche-Quinn rotation, well, okay, just substituting, one easily see that the phase disappears from the Yukawa. So if it was the end, okay, nothing really interesting. Okay, we have just a massive quark and nothing is happening. But because of the quantum nature of the theory, we know that we have to write down a path integral to define properly the theory. And one finds out that this symmetry with the charge assignment, even though the Lagrangian is invariant and the symmetry, the path integral is not. So okay, this is a bit technical, but the measure of integration in the path integral is not invariant. So basically this means that effectively the action, so the Lagrangian is not invariant effectively under this transformation. But when we do this, we eliminate this phase, but we add effectively a new term in the Lagrangian. This term, which has exactly the same form, the same structure of a theta term, so the gluon fields, but instead of theta, here we have this combination, which is the axion field over Fa. Okay? So in the end, the interesting part of the Lagrangian, so this is the anomaly. The interesting part of the Lagrangian, we have a massive fermion plus this anomalous term, so an interaction between the axion and gluons of this form. So if we go back to the original Lagrangian, we see that the interesting mechanism, for the Peche-Quinn mechanism works like this. We start with a theta angle, which is a static parameter, a number, and after the Peche-Quinn rotation, we get a dynamical object, what they call theta effective, so a combination of theta, constant, plus the axion field. So somehow we are making the theta angle dynamical, replacing with the axion field. Okay. Important point. One can easily see that this operator, you just can try to use the Peche-Quinn transformation, apply, and clearly this is proportional to A. So this is not invariant under the transformation. Okay. So this means that this operator is breaking explicitly. Now the Lagrangian level is breaking the Peche-Quinn symmetry. Okay, so if the symmetry is broken, this statement here is no longer true. So now we are allowed, and this operator will generate new terms in the Lagrangian, which are not derivative in the action. So we can generate a mass, we can generate the interaction like a to the 4 and so on. So non-derivative couplings. So we can generate a potential for the action. And this is what will happen. So if one starts from this operator, okay, there are different techniques like chiral perturbation theory, for instance. So one can derive, at least approximately, a form for the potential for the action. Okay, so one can study a potential and try to see what is the minimum. So at which value of this theta effective lies the minimum of the potential. And one finds out, computing, that the minimum lies at theta effective equals 0. Okay. So notice that also this gives rise to a mass for the action. So the minimum is 0, and this is not only a result from an explicit computation that it's approximate, but there is even a theorem, so a mathematical theorem by Waff and Witten, that assures that in QCD the minimum of the potential for this combination will always be at 0. Okay, so no matter how the precise form it is, we know that this is an exact result. So this is how the Peche-Quinn mechanism is working. So instead of having a theta as a number, a parameter in the Lagrangian, now it's dynamical, and in the minimum it relaxes to 0. So in the minimum, so where we live, there is no CP violation from a strong sector. So theta is basically 0. Okay, so this is somehow the summary of how the Peche-Quinn mechanism works. Okay, so up to now, if there were the end of the story, if there was the end of the story, then okay, we are fine. The action is let me also mention that the action, it's very interesting, because not only solves the strong HP problem, but it also turns out that it's an excellent dark matter candidate, one of the most motivated dark matter candidate. And I will not discuss this in this talk, but there is an extra motivation. Actually, So the combination of these two motivations, dark matter and strong speed problem, makes the axion probably the most motivated, or one of the most motivated dark matter candidates. So let's now see where are the problems. So the problem is that until now, I assumed, like when I showed the simple model, a simple example, I assumed that there was a global symmetry, this U1, Pechequin symmetry. I put by end from the beginning. I didn't explain where it came from. Now the problem is that global symmetries are not fundamental symmetries. Okay, so what I mean with this? Well, first of all, we know that gravity exists, and even though we still don't have a theory for quantum gravity, we know that this theory must exist. So there are some candidates, like string theories or others. And even if you are not able to do proper computation, there are still very solid conjectures based on quantum gravity. So some are based on explicit realization, like string theory or others, but also some more general arguments based on the thermodynamics of black holes. And so these are quite solid. And this conjecture states that quantum gravity must break all the global symmetry. So if you have a global symmetry of our theory, when we include the effect of quantum gravity, then this symmetry will be broken. So remember that quantum gravity has a typical scale, which is the Planck scale, which is around 10 to the 19 GeV, so it's many order of magnitude larger than the QCD scale or even the electroweak scale. So it's something that happens at so new physics at very large scale, energy scales. But this is qualitatively an important point. So our Pechequin symmetry, even if we impose at low energy, we should expect that will be broken by quantum gravity effects. So what we can do, let's take an effective field theory perspective. No? So we know that our theory, the standard model, or the standard model plus the axion, is not the final theory, but it's just an effective theory that is valid at low energy scales. Okay, so what we can do is, okay, we are at low energy, so we have some gauge symmetry that we impose on the Lagrangian, and what we can do, we write down the most general Lagrangian, which is invariant under gauge symmetry. Okay, so if we only consider renormalizable interactions, which basically, as we will see, means ignoring the effects of physics at higher scales, then if we write down a renormalizable Lagrangian gauge invariant, typically we find that the Lagrangian is invariant under some global symmetries that are not put by end from the beginning, but somehow arise accidentally. So maybe an example is the best way to show this. So this is well known. In the standard model, we impose gauge symmetry, so we have some gauge group. We write down our Lagrangian for quarks and leptons. And if we only write the renormalizable terms, dimension 4, we find that there's this extra symmetry, so acting on quarks and the leptons. So we have some new U1 symmetries, like baryon and lepton number. But these we didn't impose by end at the beginning. They just arise because it turns out that the Lagrangian is automatically invariant under this. Okay? So this is the concept of accidental symmetry, no? And so today we expect that somehow all global symmetries should arise in this way. We don't impose them, but if we just consider low energy physics, they arise accidentally. So this is somehow the first lesson, no? So if we want a good model for the Pechequin, for the axion, we should expect that this model should predict this accidental Pechequin symmetry at low energy, so at a renormalizable level. So for instance, the simpler models, like the KSVZ, are not doing this. So if we drop the assumption that the global symmetry is imposed, then one can write, even at a normalizable level, one can write terms that are not Pechequin invariant. Okay, so we need something more sophisticated. But it's even worse because, so as we saw, we know that there is new physics at high energy scales that is not described by our theory. For instance, quantum gravity. So there can be much more, of course, but at least gravity, we know that it must exist. So new physics, basically what this means. It means new particle, new heavy particles. We'll have some mass around the cutoff scale, or new interactions. In general, new particles that are dynamical only when we consider energies at the order of the high energy, so UV scale. Okay. So the question is how we describe these, the effects of new physics at low energy. So if we are just focusing on processes that are occurring at energy scale much smaller than the UV scale, so for instance the Planck scale. So if you want to describe things that happens at the electroweak scale, for example. Well, since we are describing the dynamics at low scale, our theory, our operators will contain only particles which are light enough, so particles that are lighter than, much lighter than the cutoff scale. So how we do this? We use effective operators, or if you want, higher dimensional operators, so non-renormalizable operators. So if we allow the Lagrangian to contain higher dimensional operators, these look like this. So we have some operator, we have some dimension d larger than 4, and this operator will contain only the low energy fields, so the one that are dynamical at low energy. But this operator will be suppressed some energy scale, and this energy scale will be the scale of the UV completion of the theory. So we know that when the energy will arrive around lambda UV, and our model is not working anymore, our effective theory is not working, we need to complete UV complete, including the new wave fields. So somehow this is the range of applicability of our theory. So at low energy, this higher dimensional operator will be suppressed by powers, the appropriate number of powers of this high energy physics scale. Okay, so this is the way we parameterize high energy effects from a low energy perspective. Okay, so this is quite general. It's not only for the action, it's for how effective field theory works. So this is everywhere in physics. So very, very simple example for those that are not familiar with this. So the weak interaction historically developed exactly like this. So now we know that the weak interaction has some scale, which is basically the W mass, the W gauge boson mass, around 100 of GeV. So we know that if we are at these energies, we have our electroweak theory. We can write our normalizable Lagrangian with the W, and we can compute processes like fermions, scattering. But if you are at energy much below this scale, yeah, so this is a typo. So we have energy much below this scale, that historically is what happened. We cannot use this theory, of course, because we cannot see this heavy particle. So what we can do, we can integrate this particle and write down a Lagrangian that contains only the light particles, in this case these fermions. Okay? So this is not electroweak, but this is the Fermi theory. And this is actually what Fermi did. He wrote down this kind of Lagrangian, and later on people understood that this could be complete in the UV by electroweak theory. Okay? So this is exactly, so you see, if you are at energy much below the mass of the W, this kind of process describes exactly the same physics of this one, once we parameterize in the proper way. And this is exactly the structure of the operators that I showed before. So it's higher dimensional operators, as dimension 6. And you see, in this case, the cutoff scale, so the high energy scale in this case is the W mass, okay? Because we are at much lower energies. So what I showed before, so these operators here are just the generalization of this. So now we have our theory at some scale. If we want to parameterize what's happening at much larger scales, we need to use this parameterization for the operators. Okay. So now let's allow for higher dimensional operators. Okay. As we see, some of these operators, we know that the high energy physics will break the global symmetries of the low energy Lagrangian. So at least from gravitational effects, at least. So some of these operators that we'll write down will be not invariant under the Peché-Quinn symmetry. Okay, this will break this. So this again the example as before. If we go back to baryon and lepton number, I told you that these are good symmetries of the standard model if we just focus on the renormalizable terms. But if we allow to write high dimensional operators, so already at dimension 5, one can write an operator that breaks lepton number. Okay, this is what gives mass to neutrino, by the way. At dimension 6 operator, one can write operators schematically like this that violate even baryon number. So as soon as you can write down terms that violate the symmetry. So as soon as we write down the terms of dimension larger than 4, very fast we can break these symmetries. Yeah, so this is some of the second lesson. So higher dimension operator will break the accidental Pechequin symmetry. Okay, so we should take this into account. This is not something that it's particular of some models. It's something unavoidable. For any model, we have this. Okay, so this leads me to formulate the quality problem. So let's see. So let's say that we have a model in which the Pechequin symmetry arrives at low energy. So which kind of model satisfies this is already an interesting question. We will see some example. But now let's consider that UV physics, let's say gravity for simplicity, will violate this symmetry. So as we saw, these generate operators, high dimensional operator that breaks the Pechequin symmetry. So this means that these operators are not invariant under this transformation, okay? So if we have our axiom, we transform it to Pechequin. Pechequin breaking means that this operator does not respect this symmetry. And so this means that this operator will be basically some power of the action field. For instance, some power of the scalar field, we will see. But if this operator is breaking the Pechequin symmetry, then this means, exactly as the QCD anomalous term, this will generate extra term for the action potential, okay? So when we write down the potential for the action, there is not only the QCD term, but new terms will arise from this breaking at higher energy scales. So these terms, I will show an example, but typically always this kind of behavior, they will depend on the high energy scale. And then there is this suppression factor, which is the Pechequin scale versus the UV scale to the power of d, where d is the dimension of the operator that generate this contribution to the potential. So as Fa will be much smaller than lambda, then this is a suppression. And of course you see that the larger is the dimension of the operator, the smaller is the contribution to the potential, okay? So we will see that the most dangerous operators are the ones that arise with low dimension, so 5, 6, 7, and so on. Yeah, so very generic example. We have our scalar field that transforms under the Pechequin symmetry, like a phase. And let's say that our theory allow us to write down an operator like this. So now this looks complicated, but it's very simple. You have just some coefficient, okay, the modulus and the phase. Okay, this part is not relevant. It's just some powers of modulus of phi square, which is invariant under Pechequin. But this is the important part. This operator has some powers of phi, the field phi, and clearly when we apply the Pechequin symmetry, this is not invariant. No? This is breaking the Pechequin symmetry by n units. Okay? And we see that this is quite generic. So in whatever model we write, at the end, one always manages to write down an operator which is some power of the scalar field, always. So this is quite generic. So if we plug the parameterization on the vacuum for this field, so the vacuum and the axion field, so we can just substitute this and can compute the potential for the action coming from this operator. And this typically has this form. So okay, with some coefficient, the suppression here that I was discussing before, and this is a cosine type of potential, which depends, to notice, on the phases here of the coefficient. Okay, so the full potential now will be the QCD part, okay, that it is well known, plus this new contribution coming from UV physics. Because in general, if we have many operators that break PQ, then we'll have a sum of contributions, where the one coming from the lowest dimensional operators are the ones that are more important. So graphically, it's very easy to understand what happened. So we started with this blue potential, which was just the QCD1. So we see that this, as we discussed, has a minimum at 0 in this variable theta effective. But now, if we add these extra terms, now the potential gets modified. And in particular, one finds, even doing the computation, that the minimum of the potential is shifted compared to the previous case. And in general, the minimum lies at some value of theta, which is not 0. Okay? So this means that UV physics is reintroducing again a non-zero theta angle in the game. So again, CP violation. So somehow we started with this. We had a very small theta angle that we want to explain. So this is not explaining the Lagrangian. The Pechequin mechanism relaxes the value of theta to 0. But then UV physics introduce again a non-zero value for the theta angle. Okay. So this might be a problem or not. It depends, of course, how large is the value of theta that's corresponding to the minimum. Now, of course, one could say, yeah.
Isn't that in contrast with what you said about the weak alpha theorem in that sense?
No, because you don't expect the UV theory to respect the Waffa theorem. Now,
So the theorem is only for like
vector-like theories with no CP violation, extra sources of CP violation. So the standard model is not respecting Waffa-Witten, for example. So in the standard model, if you don't take only QCD, but electroweak theory, we know that it's not a vector-like theory, and we have CP violation from the CKM matrix. So in the standard model, for instance, the theta angle is not 0. It's not correct to say it's 0, even with the axion. But one can estimate the value, and this depends on the CKM phase, and typically it's very small. If I remember correctly, sorry? Yeah, 17, 15, I don't remember, but it's well below the experimental bound. But this is interesting, no? Qualitatively, even with the action, in the standard model, theta is not 0. So, but as long as it is smaller than what we observe, we don't observe, then it's